Hello, and welcome back to the channel and episode 5 of System Design Fundamentals, where we're tackling database sharding, a powerful technique for handling massive datasets. So, what exactly is sharding? Think of it as dividing and conquering your database. Sharding splits your database into smaller, more manageable pieces called shards. Each shard is essentially an independent database that holds just a subset of your total data. This is what we call horizontal partitioning. The magic happens when these shards work together. By distributing your data across multiple database nodes, you dramatically boost performance and scalability. Instead of one database server handling all read and write operations, that workload gets distributed across multiple machines. This approach becomes essential when you're dealing with applications that serve millions of users or handle enormous volumes of data. Companies like Facebook, Twitter, and Instagram all rely heavily on sharding to maintain their performance at scale. Before we dive deeper into sharding, let's clarify an important distinction between vertical and horizontal partitioning. Vertical partitioning splits your database by columns. For example, you might store a user's profile information in one database and their settings in another. This approach is great for modular design and organizing related data together. Horizontal partitioning, which is what sharding is, splits your data by rows across multiple databases. For instance, users with names starting through M might be stored in one database, while users N through Z go into another. The key difference? Sharding significantly improves write scalability because you're distributing write operations across multiple machines. This is crucial when your application needs to handle thousands of simultaneous transactions. While vertical partitioning helps with organization and maintenance, sharding is the go-to solution when you're facing high user loads or need to serve traffic from different geographic regions efficiently. The most critical decision in sharding is selecting your shard key, the field that determines which shard will store a particular piece of data. Good shard keys include user IDs, geographic regions, or tenant IDs in multi-tenant applications. These tend to distribute data evenly and align with how your application accesses information. Watch out for bad shard key choices, like status fields. If most of your users have status active, you'll end up with one overloaded shard while others sit nearly empty. Exactly what we're trying to avoid with sharding. Your shard key needs to ensure even distribution of data and, crucially, minimize cross-shard queries, which can kill performance. Remember, once you've chosen a shard key for production data, changing it later becomes exponentially more difficult as your dataset grows. This decision will impact everything from query performance to how you handle joins between related data and maintain consistency across your system. When implementing sharding at scale, consistent hashing becomes your best friend. It's a clever technique that evenly distributes data across your shards, even as you add or remove database nodes. Without consistent hashing, adding a new shard would force you to reshuffle almost all your existing data, a nightmare scenario for a production system. Consistent hashing minimizes data movement by using a mathematical approach that places both data and database nodes along a conceptual ring. When you add a new node, only a small fraction of data needs to be redistributed, primarily affecting its immediate neighbors on the hash ring. This technique is used by distributed databases like Cassandra and Amazon's DynamoDB. It's what makes these systems elastic and fault-tolerant, allowing them to scale horizontally without major disruptions. For applications that need to grow dynamically with user demand, consistent hashing is an essential component of your sharding strategy. Let's look at a real-world example that illustrates why sharding matters. Twitter faced massive database scaling challenges as they experienced explosive user growth. Their solution? They sharded user data based on user IDs, which helped distribute the write load across multiple database servers. This dramatically reduced write latency, critical for a platform where millions of tweets are posted every hour. Beyond performance, Sharding also improved Twitter's fault isolation. When one database node experienced issues, it only affected a subset of users rather than bringing down the entire platform. This architecture proved its worth during a major database failover incident, where Twitter was able to recover without significant data loss because the problem was contained to specific shards. Twitter's experience reinforces why making smart sharding decisions early is so critical. Retrofitting Sharding onto an existing large-scale application is exponentially more difficult than building with Sharding in mind from the start. Thank you for watching this episode. In the next one, we will talk about API gateways. So don't forget to be there to learn more about system design fundamentals. Before you go, I'd love to hear from you in the comments. If you found this video helpful, to give it a like, share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.